Our next speaker is Michael Hutchins.
Okay, can you hear me? All right, so it's an honor to speak at this conference. Looking at the slideshow with all the glorious adventures, I feel like I've been wasting my life. If you a bit of a survey of what I've been wasting my life on recently. So these applications of embedded context homology. So the outline is I'm going to review 3 Floor homologies with 3 manifolds that I'm interested in. And become related. And any one sort homology is a big complicated subject, so you might wonder who needs 3 floor theories, isn't one enough? But I'll try to show that the third of these embedded context homology is good for at least a little bit, other than just being isomorphic to other things. So the 3 applications we'll talk about are some slight extensions of the Weissman conjecture, the Homology conjecture, and some instructions to embedding symplectic 4 manifolds into each other. So we're interested in 4 homology, 3 manifolds, and most of these 4 homologies depend not only on the 3 manifold, but also on the choice spin C structure of the 3 manifold. So for the purposes of this talk, let's regard a spin C structure as a oriented 2-plane field. Modulo equivalence, where 2 oriented 2-plane fields are equivalent if they're homotopic on the 3 manifold minus a ball. And if you have 2 oriented 2-plane fields, the obstruction defining such a homotopy is an element of the second homology with C coefficients. So instead of spin C structures, it's an apple space over each 2 with R coefficients in it. So here are the 3 floor theories that we're interested in. The first is Sedgwick floor cohomology. Roughly speaking, it's the homology of the chain complex. The generator of the chain complex is a solution to the Sedgwick equations on Y, or otherwise stated, it's an R invariant solution to the 4-dimensional Sedgwick equations in R cross Y. So I've already wrote down the Sedgwick equations in the last talk, so I don't have to do it. I wasn't going to do it anyway. But anyway, those are the generators of the chain complex, and then the differential counts solutions to the Sedgwick equations in R cross Y, which are not R invariant, but which, as the R coordinate converges to plus or minus infinity, converge to 2 different R invariant solutions. And then the count of these things measures the differential coefficient between those 2 chain complex generators. Then with C1 of the spin C structure is torsion, so that means C1 of this oriented 2-plane field, there's a fundamental difficulty in defining this theory because of reducible solutions, which are solutions where the spinner is identically 0. So the configuration space of pairs of connection and spinner modular case transformation is not smooth there. And so to deal with this, there's sort of 2 different ways to deal with this, and that leads to 2 different variants of Sedgwick or homology. So one of them is this HM, with a hat on it. The other is this HM with a check on it. I don't know how to make the big upside down hat as heck. If anyone knows how to do that, please let me know after the talk. Anyway, these 2 versions are related by an exact triangle, and the third term in the exact triangle is something simpler. So this is determined entirely by the reducibles, and it can be computed in terms of classical algebraic topology, namely the triple cup product on Y. So the hat and the check are deep, non-classical invariants of 3 manifolds, and the bar one is more classical. And the detailed definition of this occupies the 800-page book by Cohen and Lipto. And then another version of floor homology is the Haggard floor homology. It won't play a major role in my talk, but anyway, it's defined in terms of the Haggard splitting of Y along a genus G Haggard surface. And it's a kind of Lagrange floor homology in the G symmetric product of sigma. And the advantage of this theory is that it's very computable. who know what they're doing, I'm not one of them, the people who know what they're doing can calculate just about any example you give them. In fact, there are general algorithms. I don't know all the references, but one is this paper by Manolescu and University, which is an algorithm for computing this Hager Floor homology of any three manifold. It might take a while, but it's algorithmically computable. And then to define the third theory, I have to recall the basic definitions of contact geometry. So these are already going on the spot. Let's just say that. So let Y be a closed three manifold. The contact form on Y is a one form. Lambda says that lambda wedge is everywhere positive with respect to the orientation. And this determines two things. It determines the rate vector field. So it's in the kernel of d lambda, and that defines it up to a scalar factor. And then to normalize the scalar factor, we define lambda var equals 1, which will actually matter a little bit later. And the kernel of lambda is the contact structure, which I denote by C, that's an oriented two-plane field. And we're interested in closed orbits of the ray vector field, otherwise known as ray orbits. So these are just circles at Y, which are everywhere tangent to R, and they're allowed to be multiply covered. But aside from that, I don't care about how they're parameterized. And the contact form is called non-degenerate if all of the ray orbits are cut out transversely in a suitable sense. And this is true if the contact form is generic. So we can now talk about the embedded contact homology. So if I have a closed-oriented three manifold and a non-degenerate contact form, and I also need to choose a one-dimensional homology class gamma, and then one can then define the embedded contact homology. So this is the homology of the chain complex over Z. The generator of this chain complex is basically a set of embedded ray orbits with multiplicities. So I have a finite set of pairs alpha I, mi, where each alpha I is a different embedded ray orbit. The mi's are some positive integers, which you can think of as multiplicities. The sum of the total homology class of these ray orbits with their weights is constraints equal gamma. Now there's one more technical condition, which is that if the ray orbit is hyperbolic, then it can only have multiplicity 1. Hyperbolic means that the linearization of the ray flow around the ray orbit is real eigenvalues. So those are the chain complex generators. And to define the differential, we're going to look at holomorphic curves in R cross Y. So you have to choose an almost complex structure J in R cross Y, and there are some standard conditions which this should satisfy. So it should send the derivative of the R coordinate to the ray vector field. And it should send the contact plane field to itself, and it should rotate positively with respect to d lambdas. That's what this equation says. And finally, it should be invariant under translation of and then if alpha and beta are two chain complex generators, the coefficient of beta in the differential of alpha is a count of holomorphic curves in R cross Y. Whereas the R coordinate goes to plus infinity, if you sort of take a slice of the contact R coordinate, then as the R coordinate goes to plus infinity, then that's converging to the generator alpha, regardless of current. It has some set of circles with multiplicities. And as the R coordinate goes to negative infinity, it's converting to beta. And these holomorphic curves have to satisfy a special condition, which I'm not going to explain in detail. The name for this condition is that they have ECH index 1. Anyway, this condition forces the curves to live in one-dimensional moduli spaces if J is generic. And it also forces them to be embedded in R cross Y, except you can have multiple covers of R invariant cylinders. So that's why it's called embedded contact homology. So then, after you, since these live in one-dimensional moduli spaces, after you line out by R translation, you get a discrete set of points, which turns out to be finite in the differentials account of these. And then in joint work with Tobbs, we proved that this is actually differential. And it turns out that the homology of this chain complex doesn't depend on the choice of almost complex structure. And actually, it basically just depends on the three manifold and not on the contact form. So that will follow from the isomorphism theorems, which are on the next slide. So the three fork theories I just described are all isomorphic to each other. So the first two are parameterized by a spin C structure. The third is parameterized by a one-dimensional homology class. And so to state these isomorphisms, you need to specify how the spin C structure and the one-dimensional homology class are related. So they're related by this equation. And this makes sense because I defined the spin C structure to be an equivalence class of two-plane fields, and the contact structure is a two-plane field. And so it determines the spin C structure, which is the equivalence class of C. And then it's an affine space. The set of spin C structures is an affine space over H2, so I can add the individual gamma and get another spin C structure. So with that relation, Tobbs proved in 2008 that the embedded contact homology is isomorphic to the Sider-Witten Floor cohomology. And if you put the negative of the gradient here, I didn't explain the gradient, but if you put the negative of the gradient here, then they're isomorphic. That's relatively graded proofs. And in fact, the isomorphism is canonical, which I'll read later. And this can be regarded as a three-dimensional analog of Todd's Sider-Witten equals Gromov theorem. The Sider-Witten equals Gromov theorem says that counting solutions to the Sider-Witten equations on a closed symplectic four manifold is the same as counting certain holomorphic curves in it. And this is a version of it when the four manifold is R across the three manifolds. And then it's now known that both of these theories are isomorphic to the Hagar-Floor theory. So there's a series of papers which started coming out last year by Goodman, Conley, Tobbs, and Cohen, Eugene, Hahn, which are proving this. So when you have these isomorphisms, it allows you to transfer information between topology and contact geometry. So if you know something about Hagar-Floor, Sider-Witten floor theory, then it tells you something about contact geometry and vice versa. But before I get to that, I need to mention some additional structure on ECH. So first of all, there's a U map. This is a degree -2 map. And it's defined very similarly to the differential. So the differential counts index 1 curves in R cross Y modulo translation. To define U, you look at index 2 curves in R cross Y. And instead of modding out by translation, you require them to go through a base point. And that's a codimension 2 condition, so you again get a finite count. And that finite count is a chain map, and so it induces a degree -2 map on the homology, and that's this U. And that agrees with U maps on Sider-Witten floor homology, and I think also with Hagar-Floor homology. And there's also a canonical class in ECH. So the empty set of Ray orbits is a chain complex generator. And because of the conditions on the almost complex structure, any holomorphic curve that you're counting has to have at least one positive egg, which means the differential of the empty set of Ray orbits is 0. So it's a cycle in the chain complex, and so it determines this class, which is known by C to C. And that agrees with the contact invariance in Sider-Witten for Hagar-Floor homology. So, are there any questions about that so far?
What's the relative graded isomorphism?
So these groups have gradings, and the grading of an element is not an integer, but you just, if you have any pair of elements, then there's a well-defined grading difference. So you can say, what's the grading of x minus the grading of y? And that lives in Z-mod something. So to say it's an isomorphism of relatively graded groups means that you have two classes on one side and two classes on the other side, and the grading differences agree. There's actually an absolute grading of these theories by holotopy classes of oriented two-plane fields. And one of my students is I think, can show that these gradings agree on the isomorphism. But I won't need to know that. So what is this good for? So far there have been three main applications of ECH. One has been to the Weinstein conjecture and some slight extensions of it. Or I guess I should say these are applications of the fact that ECH is isomorphic to Snyder-Witten. And the second is it can be used to prove the Arnold-Porte conjecture in 3 dimensions. And the third is that it gives a new instructions to embedding one symplectic form manifold into another. So let me explain how this works. So recall that the Weinstein conjecture in 3 dimensions says that if you have any contact form on a closed 3 manifold, then it has at least one ring orbit. So there have been many partial results, sometimes proving more than this. So Hofer proved that if the contact structure is over-twisted, or if pi2 of the 3 manifold is non-trivial, or if the 3 manifold is S3, then in fact there exists a contraction ring orbit. Abbas, Gilly, Hofer proved that if the contact manifold has a planar open book, then there is a collection of ring orbits whose sum is not homologous. And Colette and Honda proved that for certain pseudo-enough of open books, there are in fact infinitely many ring orbits. So Todd's proved the Weinstein conjecture in all cases, and his theorem says a little bit more. So it says that if any closed 3 manifold with a contact form, and let's choose a one-dimensional homology class gamma such that C1 of the contact plane field plus twice the plane radial of gamma is torsion. And you can always do this because C1 of any oriented plane field on a 3 manifold is always divisible by 2. So you can in fact get this to be 0 if you want. But even if it's just torsion, then Todd's theorem says that there exists a finite set of ring orbits, possibly multiple cover, whose total homology class is gamma. And a very important word in this theorem says a non-empty finite set of ring orbits. And so that is a particular version of the Weinstein conjecture. And Cliff sort of described what's involved in this talk. So it involves deforming the Snyder-Witten equations using the contact form, and then you arrange that the 0 set of the spinner, the sequence of solutions, converges to the desired collection of ring orbits. There are many. It's a complicated proof with lots of Jellicoe estimates, but that's the one set summary of what's involved. And then this is sort of the first step that taught us proof that ECH is isomorphic to Snyder-Witten. And this theorem also basically follows from the isomorphism with Snyder-Witten. So let me just show you how that works to help motivate this a little bit. So Kronheim and Brunke proved that if you have a torsion spin C structure, then this Snyder-Witten for cohomology is always infinitely generated. And the proof of that, pardon me for skipping here, uses this exact triangle which I wrote down before. So, but when S is torsion, these things are all Z-graded. And this thing can be computed classically, and they prove that this is infinitely generated. And the grading, it's actually non-trivial in gradings that are unbounded in both directions. It's actually periodic. And while these other two versions, one of these has grading bounded from below, and the other has grading bounded from above. And therefore it follows from this exact sequence that these other two are also generated. So we have this non-triviality for the Snyder-Witten form cohomology. And then the corollary is that at least if lambda is non-degenerate, then for a class where gamma, where this is torsion, then there exists a non-empty ECH generator of class gamma. And the proof is that so this class here, this is just C1 of the spin C structure that corresponds to gamma. So if this thing is torsion, then the spin C structure is also torsion. So we taught this isomorphism, and this theorem of Kronheim-Brunke, the embedded contact homology is infinitely generated. Now, if there were no ring orbit, then the embedded contact except when gamma equals 0, there's the empty set of great orbits, and that's a generator. So then embedded contact topology would be Z. Either way, it would be infinitely generated, which is a contradiction, and so there has to be a non-empty ECH generator. So that's the view from 35,000 feet of Cloud's proof of the Weisser projection. Now, let me just remark that the fact that ECH is infinitely generated does not imply that there are infinitely many embedded ring orbits. So to see the most basic example, we can consider the boundary of an ellipsoid. So let's consider R4, which identifies C2. And if you pick two positive real numbers, A and B, let's make their ratio rational. Then we look at the ellipsoid where pi times C1 squared over A plus pi times C2 squared over B is less than or equal to 1. You'll see later why I put the factors applied there. Now, it's a general fact that if you have any hypersurface in R4, which is transverse to the radial vector field, so transverse to rays starting at the origin, then it has a contact form given by the restriction of this one form to it. You can calculate that the ray vector field in polar coordinates, it just rotates the two C factors at different speeds. Now, the ratio of these rotation rates is irrational, which means that if you start somewhere, there's no way you can come back where you started unless one of the two C coordinates is 0. So there are just two embedded ray orbits, one where Z2 is 0, and the other where Z1 is 0. Now, these are elliptic, which means the linearized return map along these ray orbits has complex eigenvalues. So they can appear with any multiplicity in the ECH generator. So the ECH generator are you take gamma 1 with any non-negative multiplicity and gamma 2 with any non-negative multiplicity at random multiplicity like this. And it turns out that for the ECH differential vanishes in this example. Just about the only example where it's so simple. So that's how the ECH is infinitely generated. Now, I have to make an embarrassing confession, which is that I basically don't know any other example of a contact form on a closed 3-manifold with only finitely many embedded ring orbits. The only examples I know are the ellipsoid example. You can also take a quotient of it by cyclic group action to get a similar example on an S-space. I don't know any other example. So it's possible that in all other cases, there are infinitely many embedded ring orbits. So you could ask, well, can we improve the Weisser conjecture to get a lower bound on the number of ring orbits that's bigger than 1? So we can get some slight improvements here. I'll show you the one at the bottom first. So it says if I have a non-degenerate contact form on a closed 3-manifold, and if the 3-manifold is not a lens spacer, the 3-sphere, then there are at least 3 embedded ring orbits. So 3 is a little bit better than 1, even though I like it to be infinity. Maybe the graduate student can get it up to 4, and then another even up to 5. We can get infinitely many PhD projects out of this. And this is related to another theorem, joint work with Todd. So we proved that if you have a non-degenerate contact form on a closed-oriented connected 3-manifold, and if you assume that all the ring orbits are elliptic, then in fact the 3-manifold is S3 or a lens space. There are exactly 2 embedded ring orbits. So it basically looks like the example I showed you. And these are in fact the core circles of a genus 1 Hager split, which is actually how I know that it's S3 or a lens space. And the proof of this theorem makes much stronger use of the isomorphism between ECH and cyber equipment. So the proof of the Weisser conjecture just uses the fact that cyber equipment for cohomology is not trivial. The proof of this theorem uses many additional properties of cyber equipment for cohomology, translates them to statements about ECH and their influences. In particular, where the genus 1 Hager splitting comes from is from a foliation of Y minus the 2 ring orbits by holomorphic curves, right? The projections of holomorphic curves to Y. And these holomorphic curves come from the curves that the U map is counting. So the non non-triviality to view that plays an important role here. So that's one application. Before I can talk about further applications, I have to recall some additional structure of ECH. These are the symplectic action filtration and cobordism maps. So symplectic action filtration is defined as follows. If I have any ECH generator, then its symplectic action is just the integral of the contact form over this generator. And it's sort of, well, ECH is some kind of Morse theory, or some kind of vast generalization of Morse theory, and this symplectic action sort of plays the role of the Morse function. And in particular, the differential decreases it. So if the differential coefficient for alpha to beta is non-zero, then the action alpha is greater than the action of beta. So this follows from the conditions on the Ohm's complex structure. So those conditions imply that the d lambda is non-negative on the tangent space to the point of the curve. And so this just follows from integrate d lambda over the full working curve. But since the differential decreases the symplectic action, it makes sense to look at a subcomplex. So for any real number L, I can look at a subcomplex of ECH, which is spanned by those generators that have action less than L. That's a subcomplex. I didn't know it's homology, but it's L. Now, while the usual ECH basically just depends on the three manifold, this depends very strongly on the contact form, and not even just on the contact structure. So for example, if I scale the contact form and multiplying it by a positive constant, then to get, for this ECHL to stay the same, I have to replace L by CL. So it depends heavily on the contact form. It has no known counterpart in Sider-Witten-Floor homology or Hagar-Floor homology. Now, it is true that the Sider-Witten-Floor homology is formally the Morse homology of the functional. And in Tautz's proof of the isomorphism, as he deforms his Sider-Witten equation, that functional eventually is basically the symplectic action modulo some lower order term. But for the unperturbed Sider-Witten equation, it's not clear what that Sider-Witten functional is measuring exactly. Anyway, so that's the symplectic action filtration. The next thing is cobordism maps. So there aren't really any higher categories in my talk. That's why I put the etc. here. But we'd at least like to extend ECH to some kind of TQ of T. Now, when you're looking at contact manifolds, it's interesting to think about what a cobordism should mean. So there are different notions of cobordism. The one which is relevant to this talk is what I call exact symplectic cobordism. So that's this compact symplectic four manifold, X. The value of X is Y plus minus Y minus. I call it as cobordism from Y plus to Y minus. Some people don't like it when I say that. Some people, sort of in Hagar-Floor or Sider-Witten-Floor, usually think of it as going from Y minus to Y plus. So I apologize. Anyway, in the symplectic world, it's natural to think of this as going from Y plus to Y minus. And what exact means is that the symplectic form omega X is exact, is d lambda, and not only that, but you can choose this lambda so it restricts to the contact forms on the value. So that's an exact symplectic cobordism. And the basic theorem is that if you have an exact symplectic cobordism, then it induces maps on these filtered ECHs. So here, there's no gamma here. I'm summing over all gamma. I don't care about gamma anymore. And also, I'm using Z2 coefficients, which is probably not necessary, but anyway, we're going to use Z12 coefficients. So the theorem is that you get these maps, and the direct limit of these maps as L goes to infinity agrees with the cobordism map on Sider-Witten-Floor homology as defined in Freedman wrote this book. A question?
Is it really necessary for lambda to exist on
something that is going to be a little more complicated. So the problem is that, so where I use this d lambda equals omega is basically if you input a generator here, you want to output a finite sum of generators over here, which basically comes down to the fact that you know the integral of omega over generators is controlled. So if you don't have that, then you probably have to use some kind of completion or some kind of code covering business in order to get this to work. But I think you can still do something in certain cases. Okay. So the way you would naturally try to define this coordinate map is by taking your symplectic manifold X, and well, you sort of complete it by attaching ends which look like sort of 0 infinity cross y plus and minus infinity 0 cross y minus. You want to count holomorphic curves in there. That's the usual thing. It turns out there are some technical difficulties with negative index multiple covers, so this has not actually been done. I have some ideas about how to maybe do it, at least in some cases, but right now it's not the problem. But fortunately, we can use Sadler-Witten theory instead. So the construction of this coordinate map basically uses the Sadler-Witten equations to define the map. But there's at least some relation with holomorphic curves, which is that if you choose this almost complex structure, J on the completion of X, then wherever this coordinate map is non-zero, there exists a holomorphic curve. So I'm not sure how to count these things, but they exist. And if you have two, so this coordinate map is induced by a chain map. When the chain map is non-trivial, there exists a corresponding holomorphic curve. And if you have two generators, and if the only holomorphic curve is sort of the trivial one, which looks like R cross a ring orbit in symplectization, then the coefficient of the chain map is actually 1. So that's enough for the applications. Okay, so the first application of this is the Arnold-Port conjecture. So let's take a three-manifold with a contact form. Recall that a Legendre knot is a knot K, such that the tangent space to K is contained in the contact plane field. And we're interested in rate chords of K, so this already came up in Yasha's talk. So rate chord is just a trajectory of the rate vector field, which starts on the knot and ends somewhere else on the knot, or possibly at the same point on the knot. The Arnold-Port conjecture says that every Legendre knot has at least one rate chord. So there's some partial results on this by Klaus Monke and by Kasim Abbas, but with Sadler-Witten theory, we can prove it in general. So let's try like a very trivial case of what Yasha was talking about in this talk. But here's how it works. So
This is made after the Weinstein conjecture.
right. This is sort of like the relative version of the Weinstein conjecture. So here's how it works. So you start with your Legendre knot, and you can do a Legendre surgery along K, which is due to Weinstein. So the knot K has a canonical framing from the contact plane field, which I denote by TB and K, the first American. And if you look at this framing minus 1, it turns out that if you do surgery along the knot with that framing, then what you get naturally has a contact structure which agrees with the old contact structure outside of the little neighborhood of the knot that you cut out to do the surgery. And not only that, but there's an exact symplectic coordinate from the new contact manifold to the old contact manifold. So we're going to look at the coordinate map induced by this coordinate. So let's assume, to get a contradiction, that there is no rate chord. And in order to be able to talk about ECH, let's also assume that the contact form is not degenerate. Now, the rate orbits after you do the surgery are basically the rate orbits that you had before you did the surgery, together with new rate orbits which come from cyclic words in rate chords of the knot. So for any given L, if you choose the surgery region sufficiently small with respect to L, then that's true on symplectic action L. So if there are no rate chords, then by doing the surgery in a sufficiently small neighborhood of the knot, I can arrange that the new contact form has the same rate orbits as the old contact form up to action L. And you can then use the holomorphic curves axiom from 2 slides ago to show that this coordinate chain map on ECH up to action L is an isomorphism. So basically there's a trivial holomorphic curve going from a new rate orbit to an old rate orbit. And then any other holomorphic curve decreases the symplectic action. So this chain map is an upper triangular matrix, and so it's an isomorphism. And then taking the direct limit of that, you get that the map of the entire ECH, which is a topological variant, is also an isomorphism. Now, Kornheimer-Ruffner proved that if you do a surgery along with 3 manifold Y, then the Seider-Witten-Floer cohomologies for this manifold of the surgery fits into an exact triangle where the third term is the Seider-Witten-Floer cohomology of another surgery, at least with C12 coefficients. But recall that Kornheimer-Ruffner also proved that the Seider-Witten-Floer cohomology is infinitely generated. So since this guy is infinitely generated, it's impossible for this map to be an isomorphism. Because if this map were an isomorphism, then this third term would be 0. So that's the contradiction. Now, in this proof, I assume that lamb is non-degenerate, and then you can remove that assumption by showing that you actually get a rate chord with sort of explicit upper bound on its length, which depends continuously on the project form. So if you have a non-degenerate project form, if you have a degenerate project form, you can approximate it by a sequence of non-degenerate ones and a sequence of rate chords, which converges to a rate chord. So that's the outline of that. So to summarize these applications that I've shown you so far, we've used the isomorphism between magnetic contact homology and Seider-Witten-Floer cohomology as follows. So first of all, if you just use the fact that Seider-Witten-Floer is non-trivial, then you immediately get the Weinstein conjecture. If you use more facts about Seider-Witten-Floer and translate them into facts about ECH, then you can refine the Weinstein conjecture at least a little bit. And then the fact that coordinate maps on Seider-Witten-Floer cohomology are not isomorphisms when these coordinates are given by surgeries implies a core conjecture. It's possible that you could use more information about these coordinate maps to refine the core conjecture. I don't know. Anyway, are there any questions about any of that so far? Okay, so for my last application, the last application doesn't really use the isomorphism with Seider-Witten, except that we currently need the isomorphism with Seider-Witten to define coordinate maps. But if you have these coordinate maps, then there's one more thing you can do with them, which is study 4-dimensional symplectic embedding problems. So let's consider a compact symplectic form manifold with boundary. And I want to assume that the symplectic form is exact and that there's a contact form with a boundary such that the symplectic form restricts to the boundary is d of the contact form. So this is sort of what Mike was asking about. So, for example, you could take X to be any star-shaped domain in our form. Those are basic examples. So a general question, I'll call this a Liouville domain. So if you have 2 Liouville domains, you can ask, when does there exist a symplectic embedding from one to the other? So, of course, the symplectic embedding preserves the symplectic form, and so preserves the volume forms determined by the symplectic forms. So, if symplectic embedding exists, then the volume of X0 has to be less than or equal to the volume of X1. So that's obvious. But this necessary condition is far from sufficient, as shown by the Rome down-squeezing theorem, that says that nice theorem by Deuce and McDuff solves this problem for the question of when you can embed one ellipsoid into another. So to state your theorem, given two positive real numbers a and b, let's look at the set of all non-negative integer linear combinations of a and b. So that's just some collection of real numbers. And let's write that set of real numbers in increasing order with repetitions. So for example, if a is equal to 1 and b is equal to 2, then you have 0, 1. Then there are two ways to write 2 as a linear combination of 1 and 2. It's either 1 plus 1 or 2. So I have the number 2 here appears twice. And the number 3 here appears twice because there are two ways to write 3 using the linear combination of 1 and 2. So we're down to elementary school arithmetic here. There are 3 ways to write 4, so 4 appears 3 times and so on. So, like Deuce and McDuff proves that the interior of the ellipsoid EAB has a symplectic embedding into the ellipsoid EACD if and only if the sequence of numbers for A and B is less than or equal to the sequence of numbers for C and D. So you know the kth number of one sequence is less than or equal to the kth number of the other sequence. So that's actually this condition here is still not completely obvious. So there's some subtle number theory involved in understanding what exactly this condition says. Here's a paper from Dr. Schleck. But anyway, it's a sort of a number theoretic criterion for when you can embed one ellipsoid into another. Now, the necessity of this condition, the fact that you need this condition in order for embedding to possibly exist, follows from ECH. It follows from the more general machinery of what I call ECH capacities. So the way this works is for any numeral domain x omega, this is my compact symplectic manifold boundary, I'm going to associate you with a sequence of real numbers. So the first one is 0, then these increase, and well, something they could eventually be infinite. These are called ECH capacities. So these are defined in terms of the ECH the boundary units. So you choose the contact form lambda. We use any contact form lambda is for d omega restriction. Sorry, such that d lambda is the restriction of omega to the boundary. And we say, I want to find a class sigma in the embedded contact homology such that if I apply the U map a times to it, then I get the class of the empty set. And I want to ask, what's the minimum symplectic action that I need in order to be able to do that? And I'll call it CK of x. It turns out not to depend on the other. So for example, for the ellipsoid example, the sequence of these ECH capacities is exactly the sequence N of AB, the sequence of non-negative linear integer combinations of A and B. And the reason for that, let's recall that the ECH generators are, they're two-ray embedded ray orbits. You can take each of them with any non-negative integer multiplicity. Multiplicity is N and N. The action of this generator is NA plus NB. So the actions of all the ECH generators are exactly the numbers in the sequence. And the reason why that's the ECH capacities is because the U map is an isomorphism. So it sends one generator to another until you get down to the empty set, at which point it's 0. And the U map has to decrease the action. So it follows that these generators are sort of give you these classes sigma that appear in this definition. So the ECH capacities of an ellipsoid are just these simple numbers. So the reason why this is useful is because if there exists a symplectic embedding from one of these usual domains into another, then the ECH capacities of one have to be less than or equal to the ECH capacities of the other. So that immediately implies the only part of McDuff's theorem, that if there exists an ellipsoid embedding in the sequence of numbers for one ellipsoid is less than or equal to the sequence of numbers for the other ellipsoid. So how do you prove That's a kind of symplectic cobordism between the two contact manifolds, WX1 and WX0. It's not quite an exact symplectic cobordism. It's something a little weaker. But it's enough to still induce a cobordism map on the ECH if you take gamma equals 0. And this cobordism map respects the U map and the canonical class is C. So, and that implies this immediately because the definition of this CK of X1 is the minimum symplectic action needed to find a class in the ECH which satisfies some property which is expressed in terms of U and C. So if I have such a class here with symplectic action less than L, then applying the cobordism map to it, I get a class for X0 which also satisfies the same requirement as action less than L. That's the proof. So it's very, very simple once you set it up the right way. Any questions about that so far? We can compute more examples. So you can compute so the definition of ECH capacities actually doesn't require the lever limits to be connected. So if you have a disjoint union of them, then the ECH capacities, the CK is the maximum of the sum of ECH capacities of the components where the K is now to K. And these ECH capacities not only get a sharp instruction to embedding an ellipsoid into an ellipsoid, they also get a sharp instruction to embedding a disjoint union of ellipsoids into an ellipsoid. Another example is I can take the polydisk, which is just the product of two disks in C. That's not quite a legal domain because its boundary has a quarter, but it's close enough that these ECH capacities can still be defined. And it's given by some other strange number theoretic formula, which you can write down specifically. And we can read more examples. Anyway, since people are getting hungry for lunch, let me just say a couple more things to wrap it up. So, work of Dorothy Miller proves that ECH capacities also give sharp instruction to embedding an ellipsoid into a polydisk. So at this point, you could think, well, maybe ECH capacities give a sharp instruction to embedding anything into anything else. That would be too good to be true. So if you look at the problem of embedding the product of two disks of equal area into an ellipsoid E of A2A, well, it turns out that you can only do this if A is at least 3S. But the ECH capacities give no instruction to doing this when A is greater than 1. So, in fact, P of 1, 1, E of 1, 2 have exactly the same ECH capacities. So it's a little exercise. I already wrote down ECH capacities for E of 1, 2, and then you can calculate them for E of 1, 1 and see if they're the same. However, one neat fact is that if you look at the asymptotics of these capacities, then they recover the symplectic volume. That's the conjecture, which is true in all known cases. It can probably be proved by studying Thomas' work more carefully. Is that if you look at CK squared over K, then in the limit, that's just 4 times the volume of X. So if I look at the obstruction to embedding X0 into X1, so if I take K goes to infinity, then what that instruction is telling me is the obvious fact that the volume of X0 is less than or equal to the volume of X1. Now, if these things were always equal to 4 times the volume, then in theory it would be stupid. It would tell us nothing more. But fortunately, these things, when K is finite, these things are quite different from the volume, which is why we can get some non-trivial instructions. Okay. So to conclude, here's some open questions, some of which I touched on before. So first of all, as I said, it's an open question whether if you have a contact form on a free manifold other than a sphere or lens space, do there have to be infinitely many embedded wave orbits? Another way you could try to generalize the Weinstein conjecture is to say, can I prove that there's a wave orbit with an explicit upper bound on its lensing action? So playing with the ECH velocities actually suggests that this number might be known as the square root of 2 times the volume of y, where volume is measured using the volume formula in the 2 lambda. So I haven't checked, I haven't tried too hard to find a counterexample of this, but as far as I know, there's always a wave orbit whose length is equal to this number. The third problem, which I mentioned before, is to try to define these ECH coordinate maps using homology curves instead of standard width theory. And then the fourth open question is why this ECH or standard width theory gives such good obstructions to embedding one symplectic format manifold into another sphere. So the proof that it does prove that ECH gives a symplectic construction to embedding one sphere into another. If you have it, it's really very long. It has a lot of standard width theory in it. Sort of not just the standard width theory I was talking about, but also standard width